Hello everyone. So we were talking about the Kolmogorov's hypothesis in the last class. We got to a point where we were starting to derive Kolmogorov's third hypothesis, which is his second similarity hypothesis. I just want to take a step back before we derive some of the things here and just refresh your memory in terms of what Kolmogorov's first similarity hypothesis was. It was as follows. In every turbulent flow, at sufficiently high Reynolds number, the statistics of the small scale motions have a universal form that is uniquely determined by nu and epsilon. So we are talking about the small scale motions, meaning L less than LEI. So not the anisotropic large scales. These are everything that is less than that demarcation length scale, which we assumed it is 1/6 L0. So now everything less than that, we are saying it. Kolmogorov is saying, his hypothesis is that they have a universal form, and it is determined both by nu and epsilon. And therefore, he defined these Kolmogorov scales as follows, that is shown on the screen here, which is eta is nu cube over epsilon to the 1/4, u eta is nu epsilon to the 1/4, and tau eta is nu over epsilon to the half. Now, from these equations, you obtain that Re eta, meaning the Reynolds number based on the Kolmogorov scale is 1. So that basically indicates that the Reynolds number associated with the Kolmogorov scales is very small, right? Sort of the smallest natural number, 1. Now that's one thing. The other thing is also, if you actually use these two equations, or in fact, I would say these three equations to derive an equation for epsilon, you will see that epsilon is equal to nu u eta over eta the whole squared, which is equal to nu over tau eta squared. So this is coming from here, isn't it? And this part is coming from these two. We derived this last class. This shows that u eta over eta is 1 over tau eta, which is consistent because the time scale would be equal to the length scale divided by the velocity scale. So that is consistent. So the entire characterization of the small scales is consistent. So this all indicates that these are indeed the small scales, and we have a consistent characterization of the small scales. That's where we were at. Then what we did was we considered, say, a point in a high Reynolds number flow, and let's say in non-dimensional coordinates we express it as y is equal to x minus x naught divided by eta. Here what we are doing is we are subtracting it by a reference point, but the more important thing is we are dividing it by the Kolmogorov scale. So we are normalizing it with the Kolmogorov scale. The same thing goes for the velocity difference. So the Wy is sort of a non-dimensional or a normalized velocity difference, which is u minus some reference velocity divided by the Kolmogorov velocity. So what you're essentially doing is you have now normalized it. You have now scaled it with the Kolmogorov scales. So this means that when we say that the small scales are universal, they are similar, they are statistically similar. So on the small scales, all high Reynolds number turbulent velocity fields are statistically similar. But more importantly, they are statistically identical when you scale them with the Kolmogorov scales. So that is what we are doing here. When we scale them with the Kolmogorov scales, statistically they are going to be identical. Okay, so that's where we were at when we ended up in last class. And we also derived one more thing by trying to derive the ratio of the smaller scales to the larger scale, something like an eta over L0. What did we do? So here is where I would like to show something. So if I have my epsilon, my dissipation rate, I know that it is approximately equal to u0 cube over L0, isn't it? Or it is also equal to, if you write it in terms of time scale, it is also equal to u0 squared over tau 0. Okay, be that as it may, I'll just use this part. And I know from the Kolmogorov relationship, eta to the 4 is equal to nu to the 4 over epsilon. I had it as 1/4, but I took it to the 4th power. And then what I do is now I eliminate epsilon from these two equations. I eliminate epsilon. Then what do I have? U0 cube over L0 is of the order of, or I would say it is equal to nu cube over eta to the 4, which means eta over L0 is of the order of nu cube over u0 cube, isn't it? Eta cube. Now, just so that I can manipulate this, I'll write this as eta to the 4 over L0 to the 4 is of the order of magnitude of nu cube over u0 cube L0 cube, isn't it? Because I have an L0 to the 4 here, so I brought an L0 cube on the right hand side. Now, as you will notice, this is the same as 1 over Re cube, which means eta over L0 is of the order of Re to the negative 3/4. This is the equation I have in that slide. This is what we derived last time. This is where we ended last class. So this is what I just derived. Eta over L0 is Re to the negative 3/4. I'll show you what the implications are, but I'll derive the rest of the equations, which I did not do last time. So now I'll do the same thing. I'll use the u eta equations from the Kolmogorov scale. So then what I do is, if I go back here and use this particular equation for u eta, coming back, I will have u eta to the 4 divided by nu. This is equal to epsilon according to the Kolmogorov's equations. This is of the order of magnitude of epsilon as I know it, which is u0 cube over L0. So then what I'll do is I'll manipulate this and write this as u eta over u0 because that's the ratio I want, and I'll put it to the 4th power, which means I have multiplied by an additional u0 in the denominator, which means I will have nu over u0 L0. As you know, this is 1 over Re. So u eta over u0 is now of the order of Re to the minus 1/4. This is my second equation, as I have shown here. Isn't it? One more to do. So now I will use the third equation from the Kolmogorov relationships. So, and write epsilon in terms of nu over tau eta squared. Now this is of the order of magnitude of u0 cube over L0, which is also equal to u0 squared over tau 0, because I want it in terms of tau 0. So then my tau 0 over tau eta, okay, is of the, and squared, is of the order of u0, I have it as u0 squared, isn't it? u0 squared tau 0 divided by nu. And what I do here is, this is equal to u0 squared, and then tau 0, I will write it as L0 over u0 nu. So one of them gets cancelled out, and then what I have is u0 L0 over nu. So tau eta over tau 0, I just invert it, is of the order of magnitude of 1 over Re, or I should just say it is the order of magnitude of Re to the minus half. This is my third equation as shown here. So you see what I've done here. I have eta over L0, which is Re to the minus 3/4, u eta over u0, Re to the minus 1/4, and tau eta over tau 0, Re to the minus half. This is the smallest length scale to the largest length scale, the smallest velocity scale to the largest velocity scale, the smallest time scale to the largest time scale. That is what I've done here, isn't it? These three equations, as you saw, I derived it. So what does this mean? This means that the velocity scales, time scales, and length scales, right, of the smallest eddies are very small compared to the largest eddies. Those are the largest eddies. How do I know that? Look at this equation here. It is Re to the minus 3/4. We are considering a turbulent flow with a very high Reynolds number. That means Re is a large number. A large number raised to a negative number. A large number raised to a negative fraction is going to become a very small number, which indicates that the length scale of the smallest eddy divided by the length scale of the largest eddy is going to be a very small number. The velocity scale of a smallest eddy divided by the velocity scale associated with the largest eddy is going to be a very small number again, because you have a very large number raised to a negative number. It is negative 1/4, it's still raised to negative. Same goes for a very small time scale divided by a very large time scale is again going to be a very small number. So there's a large separation between the smallest length scale, largest length scale, smallest velocity scale, largest velocity scale, smallest time scale, largest time scale. There's a large separation between that. That's the biggest takeaway here, isn't it? So in addition, as the Reynolds number keeps increasing, this separation is keeping on widening. So now what does this all mean? This takes us to the third hypothesis of Kolmogorov. So because of this wide separation between the smallest length scale and the largest length scale, because of this wide gap between the smallest eddy and the largest eddy, Kolmogorov hypothesized that at sufficiently high Reynolds number, there is a range of scales L in between the largest and the smallest. So they are very small compared with L0 on the large side, and they are very large compared with eta on the smaller side. So L is much larger than L0 and it is much less than smaller than L0 and much larger than eta. So since the eddies are much bigger than the dissipative eddies, you would think the Reynolds number here is large, and so their motion is not affected by viscosity. Viscosity has a negligible role because they are large enough that viscosity does not play a role. This is where Kolmogorov's third hypothesis, his second similarity hypothesis, comes in. In every turbulent flow at sufficiently high Reynolds number, the statistics of the motion of scale L in the range where they are much larger than eta but much less than L0 have a universal form. We knew they had a universal form, but now he is restating this hypothesis by saying that these scales have a universal form that are uniquely determined by epsilon and independent of viscosity, because they are large enough, the Reynolds number is large enough that viscosity does not play a role in these scales, at these scales. That's his second similarity hypothesis. That's his third hypothesis. Because of the wide gap between eta and L0, because of the wide gap between U eta and U0, because of the wide gap between tau eta and tau 0, there has to be a set of scales in between that are much larger than the dissipative eddies and much less than the energy containing eddies, the anisotropic energy containing eddies, that are uniquely determined only by the dissipation rate and not by viscosity. That's his hypothesis. That's his third hypothesis. So that takes us, let's look at now a range of length scales. And because of this, let's introduce this new length scale, which I am going to call LDI. And let's say since it is much larger than the dissipative eddy, so it is much less than the energy containing eddy, so it is less than LEI and greater than LDI. So it has to do with the consequence of Kolmogorov's third hypothesis. So we are saying there is an LDI that is much greater than eta. So we are saying let's say it is 60 eta. Where is the number 60 coming from? For now, just consider it to be arbitrary. I'll explain in the later modules where this number 60 is coming from. It actually will make sense. For now, let's consider it to be 60. So this is 60 eta, isn't it? And we know that LEI is 1/6 L0. So we have this range of length scales that are between LEI and eta, and let's call the demarcation length scale as LDI. Okay, so let's introduce a length scale LDI so that the range in the above hypothesis can be written as L is greater than LDI, whereas it is less than LEI. So everything in here is this universal range that is uniquely determined by epsilon and not viscosity. This entire range is determined by nu and epsilon, whereas this range here is only determined by epsilon. I want to take a step back. Remember, I have this as my characteristic length scale. L0 is the largest length scale, isn't it? Largest length scale. This is the characteristic length scale, which I was, sort of calling it as fancy L. Everything greater than 1/6 L0 is the energy containing range, anisotropic. Everything less than the energy containing range, less than LEI, or less than 1/6 L0 is the small scale, statistically isotropic and universal. So that is the universal equilibrium range. Then I have this LDI demarcation, which separates the universal range itself, which divides the universal range into two. One is dependent only on epsilon, whereas the other is dependent on both epsilon and nu. So this range here, the inertial subrange, is this range that is dependent only on epsilon. That is what we mean by this. This length scale splits the universal equilibrium range into two subranges. The inertial subrange, which is between LEI and LDI, and the dissipation range, which is less than LDI, all the way up till eta, the Kolmogorov scale. The bulk of the energy is contained in the large eddies in the size range 1/6 L0 to say 6 L0. Okay, 6 L0. So 6 L0 is sort of the largest, is sort of the maximum, and we call that the energy containing range. I hope this makes sense. So you have the energy containing range, everything below that is the universal equilibrium range. The universal equilibrium range itself is split into two, the inertial subrange, which only depends on epsilon, since we are assuming these are scales that are large enough where the Reynolds number is large, and so viscosity does not play a role, so it would only depend on epsilon. And then everything below LDI, as in that demarcation which splits the universal equilibrium range, and so everything below LDI and up till eta, not below eta. Eta is considered to be the smallest length scale. So between LDI and eta, we consider it to be the dissipation range. So this is your separation of scales. Now, given an eddy size L in the inertial subrange, so let's say L is in the inertial subrange. This is a universal equilibrium range, but only depends on epsilon. It does not depend on nu. So then you can try to find out the ratio of length scales in this range to the largest length scale or to the smallest length scale. So that's what we mean by this. Given an eddy size L, characteristic velocity scales and time scales of the eddy are those formed from epsilon and L. So I want to derive this. So I am trying to find out what U of L is. Now, here is what I'll do. So what I'll do is I'll use the definition of epsilon. Okay. Now what I know is that U of L is epsilon L to the 1/3. Isn't it? It is epsilon L to the 1/3. And how do I get that from? Where do I get that from? It is since epsilon is u cube over L, that is where I get this from. So u of L is epsilon L to the 1/3. From this equation, I can get that. So that means now if I use one of those Kolmogorov relationships, eta is nu cube over epsilon, right? Eta is nu cube over epsilon to the 1/4. And that means, and I also have u eta is equal to nu epsilon to the 1/4. Isn't it? So eta fourth, okay, epsilon to the 1/3 from here. Eta fourth epsilon to the 1/3 is equal to, now notice what I'm doing here. I am actually eliminating viscosity from these two equations. Eta fourth epsilon to the 1/3 is u eta fourth to the u eta fourth to the epsilon. This is what I have. That means epsilon from here is equal to u eta cube divided by eta. Do you see it? Eta, so from here I can obviously get epsilon to the 4/3 is equal to u eta fourth to the epsilon to the 1/3. Epsilon to the 4/3. So from here, epsilon is u eta to the cube divided by eta. So that means in here, so that means u of L is equal to u eta. Now notice what I'm doing. I'm going to write epsilon in terms of this. So u eta to the eta over 1/3 times L to the 1/3. So that means I'll have u eta L over eta to the 1/3. Isn't it? Which I can also write it as, by similarity, I can also write it as this would be equal to u0 L over L0 to the 1/3. This is how I get this equation. This is the equation that you see here. U eta L over eta to the 1/3, which is also equal to u0 L over L0 to the 1/3, because u eta becomes u0 and L over eta becomes L over L0. Isn't it? We could do something similar with tau as well. Okay, so now keep in mind my u of L, so since epsilon is equal to u cube over L or u squared over tau, isn't it? Which means I can, if I write this u in terms of L, if I write this u in terms of L over tau, then this becomes L squared over tau cube. Or tau is equal to L squared over epsilon to the 1/3. And this is what I'll use. So tau of L is equal to L squared over epsilon to the 1/3. That is what I'm going to use. And then using the fact that eta is nu cube over epsilon to the 1/4 and tau eta is nu over epsilon to the 1/2, I will eliminate viscosity from here. How do I do that? I will write viscosity here as eta to the 4 epsilon to the 1/3, and nu from here is tau eta squared epsilon, isn't it? So then eta to the 4 epsilon to the 1/3 is equal to tau eta squared epsilon, which means eta to the 2/3, isn't it, is equal to eta to the 4/3 divided by tau eta squared, or eta to the 1/3. I'm going to leave it like that because I have eta to the 1/3 here. Eta to the 1/3 is equal to, sorry, epsilon to the 1/3. I'll leave it as epsilon to the 1/3 because I have epsilon to the 1/3 here. Epsilon to the 1/3 is eta to the 2/3 divided by tau eta. I will substitute that here. So tau of L is L to the 2/3 divided by L to the 2/3, and instead of epsilon to the 2/3 I will write this as eta to the 2/3, and then I have a tau eta. That's it. So then I'll have this as tau eta times L over eta. L over eta to the 2/3. So this is your tau L, which is also equal to tau 0, L over L0 to the 2/3 by similarity. So this is my second equation which I have here, which is tau L is tau eta times L over eta to the 2/3, which is also equal to tau 0, L over L0 to the 2/3. So what I have done here is I have now shown the velocity scale associated with your inertial subrange, your time scale associated with your inertial subrange. So this, as a consequence of this second similarity hypothesis, which is Kolmogorov's third hypothesis, what we now know is that the velocity scales and the time scales, they decrease as L decreases. Because look at this value. Look at this value. If you take tau of L, which is the inertial subrange time scale, divided by tau eta, which is the Kolmogorov time scale, this is going to be L of L over eta to the 2/3, isn't it? This is a number that is less than 1. This is a number that is greater than 1 because L over eta is a larger number. Same goes for tau L over tau eta, or the inverse is true. So essentially, as the length scales decreases, the velocity scale also decreases, and the velocity scale also decreases, and the time scale also decreases. So for example, if I take u eta over u of L, isn't it? Kolmogorov velocity scale divided by inertial range velocity scale, I will have L over eta to the minus 1/3. Minus 1/3, a number that is less than 1, a number that is going to be less than 1, which means u eta is less than ul. So as the length scale decreases, when we go all the way to the Kolmogorov scale, your time scale decreases and your velocity scale also decreases. So I hope this was clear. Now we have finished out the entire set of Kolmogorov hypothesis, and we have got some very important points in terms of how the length scale decreases as the how the velocity scale and the time scale decreases as the length scale decreases. We learnt about the universal equilibrium range, the energy containing range, and how the universal equilibrium range is split into the inertial subrange and the dissipation range. So in the next class, we will restate the Kolmogorov hypothesis in terms of the joint PDF and go further and look at things like structure functions, 2-point correlations, integral length scales, and Taylor scales. Thank you.